All right, well, welcome back. We're now gonna walk through the lab on multiple testing. And of course, the first thing that we do whenever we sit down at our computers is that we should set a random seed so that you'll get the same results that we get. So here our seed is 6. And now we're gonna simulate some data, and the data is gonna correspond to 100 hypothesis tests. Each of these hypothesis tests is gonna be that the mean of a particular vector equals 0. Let's create this matrix X. And so what we have here is a matrix X with 10 rows and 100 columns. Each column corresponds to a hypothesis that we're going to test, which is that the elements of that column have mean 0. And right now, this X matrix, all of its elements are normal 0, 1. But we're going to modify the first columns of X so that their mean is actually 0.5. So that's what we've done here. We've taken the first 50 columns of X, and we've added 0.5 to each of those first 50 columns. And again, we're going to test the null hypothesis that for each of the 100 columns of X, the null hypothesis, or rather, the mean is 0.
So we can use the t.test command to test the null hypothesis on, let's say, the first column here. And you see that when we do this, we get some output. And in particular, the p-value is 0.07.
So for this first column, did the null hypothesis hold or did it not hold? I can't remember.
So for the first column, it did not hold.
Oh, the null hypothesis did not hold. But we got a p-value of what now?
0.07. So just because we get a slightly larger p-value, of course, doesn't guarantee that the null hypothesis is in fact true.
So this is actually a guilty criminal, but we failed to reject the null hypothesis that they're innocent, right?
And because we didn't get evidence beyond reasonable doubt.
That's right. There's still a reasonable doubt. We happen to know, because we simulated the data, that the null hypothesis does not hold for this first column, but our p-value doesn't show us that in this case. So that's how we're going to test the null hypothesis for the first column, but we're going to now make a for loop to test the null hypothesis for all 100 columns, right?
Yep. And so now what we're going to do is look at which of these p-values were less than 5% and which ones were greater. And so to do that, we first create a vector with 100 elements in it, each one that says do not reject the null hypothesis. And then we go through and select out the elements where the p-value is less than 5%, change that to a rejection decision. And here's the table of counting all the various possibilities. And this corresponds to the tables we were looking at in the slides. And of course, because this is simulated data and we know the truth, we can actually calculate all 4 components of that table. And so, for example, here, the situations where we manage to reject the null hypothesis, even though the null hypothesis is true, that's this 3 here. That corresponds to the type 1 errors that we had previously.
So this 2x2 table that Gareth just created for us, it looks like those 2x2 tables from the lecture, although notice that like a couple of the columns have been swapped like left, right, and up and down. So you got to look carefully to understand how this corresponds to those tables from the lecture. So in particular, though, V here, V is the number of false rejections or type 1 errors. V is what now, Gareth?
3. 3.
And why? How can we conceptualize the fact that it's 3? Like, what would we have expected it to be? If we're rejecting, so let's think about this. We were rejecting any null hypothesis for which the p-value is less than 0.05, and there were 50 null hypotheses.
So we would expect about 2.5 that we falsely reject.
So yeah, we expected to falsely reject around 2.5. We actually falsely rejected around 3. Does that pass the sniff test?
Seems reasonable.
Seems reasonable, yeah. So we have 3 false rejections, and then we can feel really happy about the fact that out of the, well, let's see. The null hypothesis was true for 50, so we had 3 false rejections, and then that means, of course, 47 that we didn't falsely reject. So that's good. But we can't actually feel so good about what's happening in that leftmost column, because out of the 50 null hypotheses that didn't hold, we only managed to reject for 10 of them.
Yep. And that was because even though they didn't hold, they weren't too far off from the truth. And so we didn't have enough data to be really sure to reject them. Remember, we only have 10 observations here for each of these hypotheses.
So like, remember, we had that p-value of 0.07. Even though we happen to know in our hearts, because we simulated the data, that null hypothesis was false for the first column, we weren't able to reject H0 for that first column. And that shows up in that top left corner here. So those are like 40 failures to reject. So the bottom line here with this 2x2 table is that out of the times that the null hypothesis held, out of the hypotheses for which the null hypothesis held, We only falsely rejected 3 times out of 50, and that's, again, what we would expect based on controlling the type 1 error at level alpha equals 0.05. So that's good news. And then the bad news that's a little bit disappointing is that out of the 50 null hypotheses, or rather the 50 hypotheses where the null hypothesis didn't hold, we actually only successfully rejected 10 times. And that's just really because for the other 40 times that the null hypothesis didn't hold, we just didn't quite have that preponderance of evidence that we need to reject at level 0.05.
And that's because even though the null hypothesis didn't hold for those 50, we were only 0.5 different. The means were only differed by 0.5.
Or rather, the mean was only 0.5 away from the null hypothesis.
Right, and so not a very strong signal, as we sometimes talk about in hypothesis testing. So let's repeat this calculation very quickly, but with a larger mean difference for the 50 where the null hypothesis doesn't hold. Instead of using 0.5, we'll use 1 here and repeat everything else. We'll recalculate the p-values and recalculate the table. And now what do we see?
Well, now I'm a lot happier because out of the 50 null hypotheses that did not hold, so that's look in the first column, H naught was false 50 times, we actually successfully rejected 41 times out of 50. So that's really good.
Excellent.
Now, what about the right-hand column though, Gareth? What's going on?
Well, so of the situations where HO was true, was actually only one time where we rejected the null hypothesis. So that's pretty good as well.
And that discrepancy between the 3 that we got before and the 1 that we have now, what can we chalk that up to?
Just a random variation in the hypotheses.
Random variation, yeah. We would expect on average, again, to be falsely rejecting the null hypothesis 2.5 times on average. So that bottom right number should be something around 2.5. It was 3 the first time.
So we got a little bit lucky
1
this
now.
time.
Yeah.
Got a little bit lucky.
All right.
Okay, so the next thing we're going to do then is talk about the family-wise error rate. And one of the plots that we showed was with this simplified calculation where we assumed that the null hypotheses were all independent from each other and calculated for differing values of m what the family-wise error rate looked like. And so I'm going to reproduce that plot here. It's a relatively simple calculation. Make a vector m from 1 to 500. And then we're just applying the same formula that was in the slides for different values of alpha. And then I'm just going to plot these 3 curves. Now we have our first plot, and our second, and our third. So these correspond to the 3 different values of alpha here. And you can see again that as m gets larger and larger, the family-wise error rate rapidly goes up towards 1, except for maybe the green line when alpha is really small, but eventually even that one would get close to 1. So just emphasizing that for large values of m, it's very hard to control the family-wise error rate. And here's the 5% cutoff. Okay, so now we're going to move on and look at those fund manager data, the 5 fund managers. And this data is in the ISLR2 library, so we're going to load in that library. And we're going to start off by looking at the data set itself has thousands of fund managers in it, but we're just looking at the first 5 here. So I've just subsetted off the first 5 fund managers. Calculated a t-test for the first of those fund managers. And you can see here the p-value is 0.006, which is what we saw in the slides previously. So this is just matching the data that we had before. We're going to calculate the p-values for all 5 of these managers. And I'm just going to print them on the screen here so you can see these again are the 5 p-values that we saw previously in the slides.
And we can see fund managers 1 and 3 have the smallest p-values, and fund managers 2, 4, 5 have very underwhelming p-values.
Definitely wouldn't stick with those ones. So now we're going to apply the Bonferroni and Holm methods. And fortunately, we don't have to be very clever in implementing these methods in R because R does the calculation for us automatically using this p.adjust function. So how does this work? So if I use p.adjust, I feed it the p-values and then I just tell it method equals Bonferroni, and it automatically adjusts the p-values, and essentially all it's doing really is multiplying them by m and cutting off at 1.
Where m is the number of tests, right?
Exactly. So in this case, m is 5. And if you look at this, all it's done is just multiply each one of my p-values by 5. In some cases, that would result in a value greater than 1. So it just caps it at 1. And just to emphasize that, I've done a little calculation here where I've just manually done the same thing, and you can see it's identical to the Bonferroni. Okay, and then just the final one here using the Holm method. Holm was a little more complicated to describe, but it's actually trivial to calculate in R because, again, we use exactly the same command and just tell it method equals Holm, and it makes those adjustments. And you can see that the smallest p-value, the one associated with Fund Manager 1, hasn't changed at all here, which is what you'll always see with Holm. But the really important one is Fund Manager 3, where the p-value using Bonferroni, the adjusted p-value, if you like, was just a bit above 5%, and now using Holm, it's a little bit below 5%. So this is why we can now reject, at least at the 5% level of significance, the null hypothesis for Fund Manager 3. Yeah. So we're happy.
We're happy. As you all know by now, I'm lazy, so I prefer Bonferroni to Holm. I know that Gareth is on Team Holm. But what I will also tell you is like 0.05, this is just like an arbitrary threshold for family-wise error rate. And like, you know, the idea that we would be rejecting for Fund Manager 1 if we use Holm because that adjusted p-value is just barely below 0.05, but using Bonferroni we wouldn't reject. That sort of shows how arbitrary these cutoffs are.
Yep.
There's nothing magic about 0.05.
But it also emphasizes that this Bonferroni number is probably, of 0.058, is probably a little more negative than it needs to be.
A little more conservative than it needs to be.
Yeah, we can be a little more sure than Bonferroni's suggesting about Fund Manager 3.
Well, I don't feel sure.
Okay. I feel a little more sure.
Well, he feels more sure than I do.
But neither of us are investing in him, so it doesn't matter. Or her.
That's true. Yeah, well, he works at a business school. I'm only going to do what he tells me to do when it comes to investing.